All right, so next up, we're going to take a look at the different phases of matter, or gases, solids, and liquids in a little bit more detail. We're going to start off with gases, which are our simplest phase of matter, if you will. All right, so here's what our model of gas is going to be like. It's like we have little gas molecules, and they're just flying around all over the place. Sometimes they're knocking against the walls of the container. Sometimes they're knocking into each other and, bouncing off. So we'll call that a gas molecule. And so what this is, it's a model, right? Real gases aren't little spheres that are flying around the place, but it's close enough. So a model is a simplified representation of how something works. And of course, that something in this case is a gas. Note that this is a simplified representation. So the real world is a very complicated place. And if we were to look at exactly what everything is like and go down to the details and the minutia of everything, it would take way too long to figure out everything. And so when we use these models, basically what we say is close enough is kind of good enough. Right. Same way, like, if somebody asks you how old you are, you might say maybe you're, I don't know, 32 years old. You wouldn't say, 32 years, 3 months, 2 weeks, 8 hours, 20 minutes, 13 seconds, and so on and so forth, right? At some point, you're getting too detailed, and a simplified look is good enough. So the same thing we're doing here with gases. And again, what we're assuming is we have these little balls flying around in space. And so this is what's known as kinetic molecular theory. Right, that's our model of the gases. And this is something that was revolutionary when it first came out. But nowadays, since we already view things as atoms and molecules, and you have as you've grown up in pop culture and whatnot, it's not really that revolutionary, and all of it kind of makes sense. So the first thing that Kinetic KMT says is that gases are particles in constant straight line motion. So they go in a straight line, they hit something, they'll bounce off of that, but they don't do any kind of curves. They don't, orbit in ellipses or anything like that. They just go in straight lines. Number two, and this one's very important, is that the particles don't attract or repel one another. So we can think of them as perfect billiard balls. You know what a billiard ball is? Like a pool ball, right? When you play pool, they don't attract one another. They don't repel one another. We know this isn't true in real life, but because gases are so far apart from one another, it's true enough. Number three is that there's a lot of space between the molecules. Right, so if we look at our kind of model here, right, you can see there's plenty of space between any of these molecules. And so since they don't attract or repel one another, and since there's a lot of space between them, a lot of the physical properties of gases are the same no matter what gas. And this empty space explains a lot. Right, there's a lot of space between molecules. There's empty space. That tells us the gases can compress. Right, we can reduce the volume of this without messing with the molecules. There's plenty of empty space that we can remove from it. And that's not true for solids and liquids, right? Solids and liquids you cannot compress because the atoms are so close to one another. In a gas, they're pretty far apart. And then the number four thing is that the average kinetic energy of the molecules, right, so how fast they're flying around in space, is equal to their temperature. Right, so as we increase temperature, right, as you get hotter and hotter, your molecules move faster. right? Nothing revolutionary, nowadays in, 20 whatever it is right now, terminology, but back in the day, this was, somewhat revolutionary. And so if you combine all these together, we can explain a lot of the properties of the gases. Like we said, the compressibility is explained by the empty space between these molecules. They assume the shape / volume of the container, right? Since they're just little particles flying around, they're going to fly around as much as they possibly can until they hit the wall of a container. And the low density of gases as well, right? Gases are not very dense, and that's because they have a lot of empty space around them, right? So nothing too revolutionary, but we're building up our model, and we can see how we can apply that to different things shortly.